All right, welcome back. So, did you guys have fun with the crack detection? Okay. Let's see who's winning. Okay, let's look at the leaderboard. All right. We have 0.5, 0.1. 0.5 is the lowest you can score. So I guess we're still waiting for people to make submissions. All right. So today we're going to be talking about physics-informed neural nets, or PIN. So this is our kind of first time starting to incorporate physics finally into neural networks. So neural networks are, by default, very data hungry, especially deep neural networks. So in case of computer vision applications, we have ImageNet, for example, from which you can, download millions of images, and you can pre-train your model with the ImageNet data set. And then, not only ImageNet, but also there are many other, computer vision data sets available out there. So training a neural network and finding, necessary data isn't necessarily a problem. Same thing goes with the medical imaging. So, in the field of medical imaging, there are also lots of publicly available, images. For example, the one over here is the NIH chest X-ray data set, where you can find. I'm blinking on the exact number, but around 500,000 chest X-ray images with high quality labels and all that. So, people have accumulated a lot of data over there as well. So you can, use those data sets to, pre-train your model, and then, you can always start from there. Versus, in many physics applications or scientific applications, that's not necessarily the case, right? Data can be, quite expensive, and the whole process of producing data is, quite expensive as well. So, like, let's say you're interested in, CFD simulations, then, you know, depending on the complexity of the problem, um, uh, an instance of fluid simulation can take, somewhere between a few hours to, several days, right? Depending on the size of the problem, especially if you have some, complex boundary, high speed flow, then you're going to need to resolve your, space and time in a very fine grid. And, the computation can easily be, several days or weeks. Um, or let's say you're a material scientist interested in, some materials, and then again, an experiment can take forever, right? Just for setting up an experiment can be, a day or two, and then you run an experiment, you change the setting, and then you have to, so data is not necessarily, cheap in the applications that we're considering. So, that's kind of one of the problems that I want to point out, and that's kind of what creates the gap between, uh, neural networks, which are mostly developed in the field of computer vision and medical imaging, those kind of places, versus and it doesn't necessarily have any, constraints, or it doesn't follow any, governing equations or principles. And what that means is, once the model is trained, you cannot really, trust if the model prediction is reliable or not, you know. So instead, for the applications that we're considering, we would like the model predictions to, to comply with governing laws, boundary conditions, and other, physical constraints, is kind of our hope here. But we still don't know yet how to make neural networks work in that way. So the idea of physics-informed neural network, or PIN, P-I-N-N, is to fit a neural network to a solution function of some governing, differential equation describing the physical process. So that's a lot, to unpack. So instead of, looking at the high level conceptual stuff, let's actually just take a simple, more specific example, which is the harmonic oscillator. This is not necessarily a PDE. It's an ordinary differential equation, and this is something that you should have seen already in the undergraduate level. So let's say you're interested in modeling an harmonic oscillator using an artificial neural network, where the goal is to find the position. Okay. Find the position of the mass at time t. Okay, and the position of the mass at time t, which is denoted as x, has this relationship. So this is the physical rule that this thing should follow, given that we have a spring with the spring coefficient k, and then a damper c. Then we have this ordinary differential equation that goes the acceleration of the mass should be the same as the damping c times x dot, the velocity, plus kx. This is Hooke's rho, right? And then for this ODE, we consider initial conditions where we have some initial position x0, and then some initial velocity v0. And then given those initial, position and velocity, what's going to be the position of the mass at an arbitrary time t is the question that we're interested in answering. So this is one thing that you can try to do, right? To model xt as an artificial neural network, where the input to the neural network is the time t, and then the output of the neural network is the position x. Okay, and you can have how many number of hidden layers and how many number of hidden neurons you want to have inside of the neural network, but without the loss of generality, we're going to just call it model weight data. Okay, so from a given t, we have some weights, theta 1,1 through theta 1n. So that's the first layer. And then we produce some hidden outputs. And then those hidden outputs are then assembled again to produce yet another hidden outputs. Right? Sure. Yes. Well, we're going to assume that the initial condition is given. X0 and V0 is given. Given and fixed. Given and fixed. Yes. So that's actually one of the limitations of PIN we're going to talk about later. So right now we have a fixed set of initial conditions and it's not changing. And then by fitting this, what we would like to do is to just evaluate the position x at any given time t. Okay? So it's a prediction model just for that particular system with a particular set of initial conditions. And then, starting from this, we're going to expand to, other situations where what if we start from a different initial condition? What if so, those weights will, further transform this hidden states into a new, set of hidden variables. And then at the end, finally, they get combined, and then we have a prediction of the position. So, we assume that there's some ground truth. Okay. So it can be from either experiment or, numerical simulation. Doesn't matter, right? Some ground truth is given. And then, we want to fit our model, which means that, we're going to compare the ground truth and the model prediction, and we're going to define the training objective. So up to this point, we already know, right? This is the usual neural network regressor, right? And nothing really, terribly, interesting going on over here. Now the fun begins, and the interesting idea of physics-informed neural network is in the fact that we actually go further from here and take the derivatives of x with respect to t, as well as the derivative of dx dt, which is the second order derivative, the acceleration. Okay. And using those, what we're going to do is to construct yet another loss term called the physics-informed loss. Okay. And the physics-informed loss is nothing more than the residual of the governing ODE. Remember that? This one over here. So what we're doing here is to model X, right, using an artificial neural network. If that X is perfect, then it has to be 0, sharp. But since X may not be perfect, especially at the beginning of the training, we're measuring the residue, the size of the residue, okay? And then, what physics-informed loss says is to minimize that residual, okay, during the training process. So you're not only minimizing the data loss, but also minimizing the physics-informed loss, or the residual of the differential equation, okay? And if you train in this way, you should be able to train the neural network in a more reliable manner, is the argument of Rice et al., who proposed this idea of physics-informed neural network. Questions so far? Good. Now the issue is, how do we compute the derivative of the neural network? Okay. So we sort of know, right? We sort of know how to take derivatives, how to take gradients, right? From the backpropagation session, right? So, actually the method for taking the, differentials for the neural network output is actually pretty similar to backpropagation. Before that, let me mention a few things. So the notion of derivative, I mean, this is a theoretical definition of derivative. So if you have a function f, and you want to take the derivative of function f at a given x, then this is essentially the definition of how you take the derivative. So as the, you know, the range H goes to zero, then you know, the line will, you know, start to approach to the you know, the one that is tangential to the curve at f equals to f, sorry, fx, and that's how we define derivatives. Now, numerical derivatives, you know, if you're from I guess most of the engineering majors, you probably know how to take the numerical derivatives. Just as a recap, what happened to the slide? Just as a recap, you know, there are a few, you know, ways of thinking. So probably the easiest thing is to, you know, to stick with the original definition of the derivatives, right? The continuous definition of the derivatives, except that because we cannot, you know, consider like infinitesimal quantities and things like that inside of computers, we replace H with some sufficiently large, I mean, relatively large, but still sufficiently small, you know, segment data delta X. And in that case, we can approximate the dy dx using this formula over here. And depending on how you view this, you know, there can be many different ways of taking their, you know, derivatives. So for difference, you know, you go forward by delta x and then subtract the, you know, the function value at the current point divided by delta x is the forward difference. Backward difference is the opposite. You go back by delta x and you subtract that value from the original f, you know, the original fx, and then divided by delta x is another way of you know, approximating the derivative dy dx, which is called a backward difference because we're going back. Or if you know, feel hard to decide between the two, then you can just take the average between the two, which is called a central difference. Because if you actually take the average of the two, you know, usually those are kind of the ways of computing derivatives in the traditional numerical analysis literature. So, you know, FE solvers, you know, finite element solvers, you know, fluid dynamic solvers, you know, you name it. They all sort of rely on, you know, a certain type of different scheme like these. The problem is those are not the actual derivatives. We're only approximating is the first thing. The second thing is that the computation of this takes time. I mean, you have to evaluate, in case of central difference, you have to evaluate the, you know, the value at the forward, you have to evaluate the value at the backward, and then, you know, divide it by delta x, right? In 1D, right? If x is one dimensional, you know, quantity, then you just need to evaluate the function, you know, 2 times, and then divide it by delta x. But what if x is n dimension? Then it's going to be exponentially many combinations that you have to evaluate. The situation with the forward difference and the backward difference is slightly better, but not terribly better than, you know, this one, because again, you have to evaluate the function value at the forward, right? And then, you know, subtract the value that you already know, divided by delta x. And again, if it is 1D, maybe it's simple. 2D, yeah, still doable. 3D, okay, not bad. But then if you go, you know, much higher dimension, then you know, you're going to need to start worry about the computational efficiency. So, that's where this thing called an automatic differentiation comes in. And automatic differentiation is pretty much the same as the backpropagation. So if backpropagation made sense to you, we covered that already a couple of days ago. If backpropagation makes sense, then automatic differentiation should also make sense to you. And as a matter of fact, backpropagation is a specific case of automatic differentiation. So it's called a reverse mode automatic differentiation, and that's equivalent to backpropagation. But automatic differentiation is a little um, more generic concept. So it's a superset of backpropagation. So we're gonna talk about that, in the lecture, and then we will actually see how the automatic differentiation can be done in PyTorch, after the break. So just as a recap, the idea of backpropagation was basically the chain rule, right? So in the forward path, you not only calculate the actual value z, which is the result of an operation, but in the meantime, the analytic derivative that you know already, from that analytic derivative of this operation, you compute the local derivatives and store them in the computational node. And then later on, when you want to take the derivative of something, you go from the end, go backward, multiply the value with the local derivative, pass along, and so on and so forth, right? So we saw this particular example, right? Where we have a perceptron, right, with two input variables, x1 and x2, that goes into sigmoid. So FW of x is a very simple perceptron model. And then the computation graph looked like this. And then, last time we saw, how the values backpropagate, and then we sort of validated. Now, there are some, limitations with the way that we calculate the gradients. The first thing is that you always need to keep the intermediate data in the memory, which means, like in this bin, you have to memorize things, right? Each time you do the forward path. And in terms of repetitively computing things, computing gradients, that may not be the most desirable thing to do. And also, this is, I think, a more important question to ask. The backpropagation, all right, I mean, we can, we know how to take the derivative using backpropagation. It works great for first order derivatives. But what if you need a second order derivative, like in that harmonic oscillator example, right? Yeah. So this kind of implementation is great if you just need the first order derivatives. But if you need higher order derivatives or something else, then this is going to be limited, because from this current configuration, there's no practical way of backpropagating and then computing the second order derivatives. So that's where the automatic differentiation come in rescue. So the beginning of the automatic differentiation is the same in the sense that we construct a computational graph like this. Now, in automatic differentiation, we not only construct the graph that looks like this, but we also construct a graph for the derivatives. So, for example, this node over here, 1 over x, okay? We know that the analytic derivative of this is negative of 1 over x squared. So what happens inside of the automatic differentiation engine or autodiff algorithm is to create a node that corresponds to -1 over x squared. Okay. And that node, notice that is connected to the node that is prior to the original node. And then similar to the back propagation, we're going backward by one step. And for this one, the derivative is just one scalar, so nothing interesting going on. Nothing interesting going on, but that one is created as a node, okay? And that gets connected to the -1 over x squared node, okay, in this manner. And then we further go backward. We have the exponential, and we all know that the exponential, the derivative is exponential itself. So that means we're going to need to create another. We're going to need to create another exponential node, or we could also just utilize recycle the existing exponential node, right, and multiply that with the output of the, of this node over here. Now we go back one step again, and then we have the negation node, which is the same as multiplying, negative of 1. And then the derivative of this is -1. So, we create a -1 node over here, and then we, connect it to the output of the exponential multiplication. Again, another boring node that has the derivative of 1. So, and then after that, we have the result B. All right. So at least one of the derivatives of f with respect to B is identified in that way. We further go up. And over here, we have another addition node. So I'm not even going to bother to, create. Actually, I could have just skipped this, right? But for the graphical illustration, I put it over there. But from now on, I'm not even going to bother to draw that node. So we can just ignore that one. The multiplication node over there, we know that W1 times X1, if you take the derivative with respect to W1, the derivative is going to be X1. On the other hand, if you take the diff with respect to X1, then the derivative is going to be W1, right? So what happens over there is, we basically multiply the value of this node to produce the df dw1, right? And then, similarly with this multiplication node below, we do the same thing. So the result over here is going to be multiplied by this to define df dw2. And that is, so that is essentially, how the additional computational graph for taking derivative is constructed. So the difference between what we saw already and this new method is that what we saw already, right? We construct a computational graph and directly flow the number, and then we back propagate the number. In this case now, when we back propagate, we're not really propagating numbers or anything, but we're constructing another set of computational graph that is connected to the original graph. Now that we have a graph constructed like this, then computing the derivative, computing the gradient is as simple as just flowing the numbers, right? And then you can just flow the numbers through this graph, blah, 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 right? Do all the computation. And then at the end of the day, you should be able to, compute the derivatives and everything. In case you want to compute the second order derivatives, what you need to do is to simply just follow what you've done, but starting from the end nodes, the leaf nodes, sort of back propagate from there to add yet another set of graphs. And that way we can have a second order derivatives, third order derivatives, fourth order derivatives, and so on and so forth. Does that make sense? So that's really it. Yes, sorry. Well, in the exact same way. You start from here, go back, multiplication, nothing interesting going on, right? So go back. Actually, the only thing that's interesting is the exponential, right? Exponential and this one, right? Everything else, taking derivative is going to give you a scalar. So you go backward, backward, backward. Now we have an exponential node whose derivative is yet again exponential. So we're going to reuse this exponential node yet again for the second order derivative. And then backward, backward, backward. Here we have negative 1 over x squared. And you take the derivative of this, right? And then that is going to be another node added, right? So you're just keep adding the nodes depending on yeah. Okay. So AutoDiff, a few remarks. AutoDiff is not a finite difference or numerical derivatives. Same thing as the backpropagation. In the backpropagation, we saw that backpropagation is strictly the chain rule. We're not approximating anything. So up to numerical precision, you can have the exact theoretical derivative, right? So same thing, AutoDiff being the generalization of backpropagation, we're calculating the exact derivatives. We're not approximating or anything. So there's no concern of, less concern of numerical error, right? And things like that. Again, AutoDiff is efficient, maybe not as efficient as the process of just flowing the numbers back and forth, because now it involves the creation of computational nodes and all right. And then like I already mentioned, Autodiff is accurate and numerical is stable. So those are the advantages. One thing to note is that the automatic differentiation is not a symbolic differentiation, if you know what that is. Symbolic differentiation, solvers like MATLAB and Mathematica, there are ways of, computing what's called a symbolic differentiation. Symbolic differentiation is what you do as humans, right? And then there are algorithms for doing symbolic differentiation. And autodiff is not symbolic differentiation. Although using autodiff, you can calculate symbolic differentiation. So that's kind of a neat thing. So with that being said, the goal of auto differentiation is not to come up with a formula, right, for the differentiation, but to construct a procedural graph for computing derivatives. Yes. Sorry, I didn't understand your question. Okay. That's a very good question. Okay. Yes. So in case of ReLU, the second derivative is going to be 0. So in that case, the node, the 0 node is going to be created, and then with whatever value flows through that 0 node is going to be 0. So that's why when I was talking about activation functions yesterday, I told you to be careful for physics applications. So for example, if you design the network with ReLU for that harmonic oscillator problem, then the chances your network is not going to converge very well, because the second order derivative is always going to be 0. You see what I mean? Yeah. Leaky ReLU is still the same situation because we have the constant first derivative, and then from there it's 0. Exponential, yes, is better, and that's why I mentioned yesterday that ELU, yeah, maybe it's just a pedantic approximation of the ReLU in a smooth form, is what I mentioned. So from computer vision perspective, that might be right, but from the perspective of physics informed neural net, you probably want to use exponential ReLU as opposed to the usual ReLU, is one thing. Or 10H is still a good choice, right? Automatic differentiation is that you can actually generalize this to arbitrary types of functions. So vector valued function, some multivariate input come in, and then the function spit out a vector as opposed to a single scalar. We're gonna come across a situation where we compute the Jacobians. So a Jacobian is the derivative of a vector valued function, as you've seen from, I guess, calculus or somewhere, right? The definition of Jacobian is as follows. Each rows, okay, correspond to essentially the gradient of one component of that vector value function. So the vector value function, let's say, has m outputs, then each row is essentially the gradient. Okay, so f1 with respect to x1, f1 still with respect to x2, f1 with respect to xn. So that's the gradient for function f1. And then we basically stack up the gradient. That's how we get the Jacobian. Jacobian being simply the stack of gradients, the same properties will apply. The chain rule still holds true, except that now we have more indices and more terms, so you need to be a little more careful. But the same principle holds true over here. Now, one of the practical consideration over here is, in case you have a vector value function, then a naive thinking will lead you to the computation of the entire Jacobian. But if you think about it, this can be problematic. So later we're going to see the situations where the neural network is expected to output some large m dimensional outputs, and then as an input to the neural network, yet again we have some large n dimension. So the m by n Jacobian can grow really large, right? Sometimes the input to the function and the output to the function can be image, right? So if it is an image to image mapping, then you have some million of pixels, and then as an output we have some million of pixels. In that case, the Jacobian is going to be million by million matrix, which is going to be not only impossible to compute, but also just creating the memory space, allocating the memory space for that. Any regular GPUs won't be able to have that much of a space. So usually in the relevant literature, we consider what's called the vector Jacobian product or Jacobian vector product, depending on who's talking about this one. The idea is that for instead of computing the entire Jacobian, we instead compute the product of a vector and Jacobian, so that we don't have to explicitly construct the Jacobian itself. So the VJP, vector Jacobian product, we're basically considering, well, let's take a look at the example. So we have, let's say f, which is an exponential. So NP is numpy, but you can replace it with PyTorch. Let's say you have, some function g of x, which then goes into the exponential function. And then let's say the function f is the composition of the exponential function with the g of x. The Jacobian of this will then be, partial f partial g, okay? Which in this case is a, is a diagonal matrix whose diagonal components are exponential of g1 through gn. Now, in this particular situation, we sort of see that the Jacobian is zero everywhere, right? As far as this particular function is concerned. So, since our idea of computing the automatic differentiation was to construct a graph, right? And for each of the nodes, we're taking the local derivatives. What that means is for each of the nodes, if you take the naive approach of computing the entire Jacobian, each of the node you'll be creating something like this, okay, where we have lots of inefficiency here. It's simply a Jacobians are simply a matrix, filled with zero everywhere except for the diagonal. So instead, at each node, what happens is instead of computing the entire Jacobian, we compute the Jacobian vector product or vector Jacobian product, where for a given arbitrary function g, okay, we compute the computational graph for the VJP, okay, which is the result of multiplying this to this, right? And then store only this part, okay? And then whenever, we have function g that comes in through the back propagation, we just need to take the derivative of this guy and then, plug that into the BJP, as opposed to keeping this entire thing at the node, right? And then keep track of all this entire Jacobian unnecessarily, inefficient manner. So, yes. So, one thing I want to make sure is that this is typo. I don't know how the prime ended up over there. Ignore the primes. We're using the chain rule. So if you were to use the chain rule in an exact, mathematically exact manner, you will need to use the Jacobian, right? But like I said, storing the Jacobian itself is computationally inefficient. So let's compute an intermediate product here. And then we'll start from this intermediate product. And then whenever, some G flow in, then, substitute the G values. And then you have the vector Jacobian product. Well, yeah, so same thing. Let's go all the way back. Yeah, if you look at this local node, I don't really care what kind of crazy things happening over there. So no matter what that is, when we back propagate, there's a single number coming in, right? And then we can still handle it. So we're sort of limiting the scope to a single node with some generic value G is what's represented over here. The G can be anything, can be a result of computation from other nodes. And then finally, when it arrives here, then we just substitute the values. Other questions? It should be G, not G prime. So let me fix that. That's a typo. My bad. Yeah, it should be this. Okay. So there are many, auto differentiation libraries. And this is where kind of the terminology start to be kind of mess. The name of the auto differentiation library is called AutoGrad, automatic gradient. And then, people start to have a confusion with AutoDiff, AutoGrad. I think it is almost now accepted as a synonym. So autograd, autodiff, but I guess I try to be more precise about what I refer to. So autograd is a numerical library that implements autodiff, automatic differentiation. You can feel free to play with this particular tool, although PyTorch has its own version of AutoGrad. The torch.autograd is actually what we're going to use today. But there's a Python native, and not Python native, but there's a non-PyTorch version of automatic gradient or automatic differentiation called AutoGrad. AutoGrad can be imported like this. It's a very clever way. So if you import autograd.numpy as np, then the usual numpy code, okay, turns into something that's compatible to autograd. And what that means is, the code that you have already written in numpy, you should be able to take the gradient, take the derivatives of those functions. So like over here, it's the usual 10H implementation with NumPy. And by importing autograd.numpy like this, now this turns into, from the user side, there's not much of a difference in the syntax. The syntax is, as a matter of fact, exactly the same. But internally, in terms of the way that the computation is performed, now there's the internal computation of graph constructed and so on and so forth, so that, when you do the grad 10H, now you create a gradient function for 10H, okay? And then that function, again, is a function, so you can just throw in a number like this, and then it will evaluate the gradient of 10H in that manner using the automatic differentiation algorithm. So this is really a fun and useful library to know of. In PyTorch, this is where we switch the gear a little bit and then go to the Jupyter Notebook. So Colab, search.google.com. Yep. So here we are. As usual, I'm importing Torch. And let's say X is my tensor. um, oh, sorry. This is something that I'm still confused. But there's a lowercase t and a uppercase t. Lowercase t is for starting a creating a tensor with a scalar value. All right, so here, what we're gonna do is similar to the example that we saw. We'll define our own version of 10H. Which is exponential of minus 2x. And do this. So as a result, we get 0.7616. Okay. Now, let's start with the thing that we already know. So from here, using backpropagation, how do you compute the gradient? How do you compute the derivative of 10H? So this is something that you already know, right? You just need to y dot backward. All right. Yeah. So you trigger the backpropagation, and then after the backpropagation is done, the gradient is stored, or the derivative is stored at x dot grad. Correct. Of course, in order to be able to use this, you have to turn on requires grad equals to true. You have to run this again, actually. But y that backward will give you the gradient, which is 0.42. Now, this is the usual way of computing the backpropagation. And then we'll start from here. We're going to look into the ways of computing the automatic differentiation. But before we get there, one important note I have is that y that backward is for one-time use only. Okay, so usually when PyTorch construct a computational graph, it is it cares about it is mindful of the memory consumption and all this kind of stuff, because neural network computation can be very expensive. So PyTorch does move diligently in the background, and whenever a computational graph is used, then it'll destroy it so that it doesn't occupy the memory space anymore. So what that means is I just ran y that backward over here. If I were to run y that backward one more time, then it's going to complain. It's the same exact code, but second time I run it, I have the runtime error. And if you go down and read the error, then it actually says trying to backward through the graph a second time. Okay. And it's impossible because the graph has been already destroyed. And it even suggests the way of fixing that problem, which is the retain graph true option. So here, when you do the backpropagation, if you plan to do the backpropagation for whatever reason multiple times, then you want to set retain graph equals to true, like this, and then run it. So since already, I messed up my computational graph, I'm going to go back up and then start over from the beginning. So I just, created a tensor, define a 10H, and then define my Y. And then when I do the backward, I run it here, still the same result. But over here, previously, remember, it returned a runtime error. This time, it runs. Okay. Now, do you guys find anything crazy, though? What is that? Yeah, the value is not the same. What just happened? Oh, shit. Well, since I already got the error, so I ran this one and then crawled back up, ran this one again. Now there's a runtime error because the second time I ran backward, I didn't turn on retain graph, right? So it has already destroyed the computational graph. So by the time I run backward third time, now it complains. Okay. But that's not what I wanted to show you. What I really wanted to show you is here. So when I first run this, it's 0.42, and then I run it one more time. It's 0.84, 1.26. Let's keep growing, right? And you probably noticed that the pattern of growth, we'll keep adding 0.42 on top of the previous value. So we have 2.1. So the next will be 2.52, I can guess. Yeah, 2.52 with the numerical precision, and so on and so forth. So, yesterday, some of you actually asked the question about why do you have to reset the gradient? Remember yesterday's code, there was a part where, you had to reset the gradient during the training session. So this is kind of the same thing, but now I think we can go, further into what's happening over here. So the graph, okay, when you construct and then flow the values once, then there are values remaining from the previous execution. And then PyTorch is intentionally lazy, okay, and do not clean up those values, because cleaning up itself can take some computation, right? You have to visit all the nodes and then clean up the values, empty the bin, right? Instead, PyTorch is intentionally lazy to save the computational time, which means the ghosts from the previous execution will stay in the bins. So the next time you run y the backward again, the numbers will be added on top of the existing values, and then you start to accumulate like this. So because of that, what you almost always have to do is to zero out the gradient of x. And by calling this, you're, emptying and cleaning up the, the previous execution and set everything to 0 so that you start from a, fresh new state. And in that way, you can get the actual, real gradient value. And now that I added that x.grad.0, no matter how many times I run this, I'll still get the same output. Any questions? Now, here's one more thing. Let's take the derivative of second order derivative of 10h. Okay. So why that backward is obviously the back propagation, but you can have an option called a create graph equals to true. Okay. And what that does is exactly what we learned today. Instead of just passing the values, now with that option, we're going to create a graph, which is the automatic differentiation. Okay. So that's the PyTorch syntax. Now, as a result of the first, pass the back propagation, x dot grad is going to be where the gradient value is going to be available. And I'm going to call this a dx. Okay. Now the dx, this is how you compute the second, derivative. You do dx dot backward. Okay. And then, dx square is x, dx, not dx, x dot gradient. Okay. And in that way, you can compute the second order derivative of the 10h function. So you initially have a computational graph for 10h, right? Which is y. And then y that backward by default will just compute the back propagation. But if you turn on the create graph equals to true, then instead of simply just back propagating the numbers, it'll create a new graph. And through that graph, it'll do the back propagation, right? And then compute the gradient. And x dot grad is going to store some number, right? But that number, okay, which we decided to call dx, is now the result of flowing numbers through a graph that we just created. What we do is to do the back propagation from that new graph all the way down to x again, because we're taking derivative with respect to x, right? Two numbers. Actually, 10h is not a good example. So let me do something else. So x torch.tensor and then ry. Let's just call this x squared. Okay, so we all know how to compute the derivative of x squared, which is 2x. And then, if you take the derivative one more time, it's 2. So if you do this, we'll get this, which Does it look accurate? So we have x equals to 1, okay? And then y equals to x squared. So the first derivative is 2x. So it has got to be 2. The second derivative is 2, no matter what, right? But we have 4. What's going on? Should I change the number to 3? So first derivative is 2x, which means that the result should be 6, right? And then the second derivative, regardless of the input, it will still be 2, right? But we get 8 and 8. It's weird, huh? There are two things going on. The first thing is, which one should I start? Let's start with this one. In Python, this is the part that I don't like about Python, which is that when you do, dx equals to x dot grad, this is an assignment operator. If you're from C++ or other traditional languages, assignment is an assignment, right? But in Python, the assignment can be sometimes a reference, okay, or the notion of pointer. And there's no explicit syntax there, okay? In case of C++, for pointers, you put an asterisk or the ampersand to make sure that this is a reference, this is a pointer, right? All the kind of good stuff. In Python, all of this are handled behind the scene, okay? So what's happening over here is dx is like a pointer, okay, pointing x dot grad. Result x dot backward, the value of x dot grad has changed, okay? So dx2 is yet another pointer of x dot grad, all right? But pointing the same thing, and therefore, first of all, the values of the two are exactly the same. So for that, a simple fix is to do this, x dot grad dot clone, okay? And then if you run the code, now over here, we're actually assigning the value. So dx is now the clone instead of just simply a pointer, but it's a clone of, x dot grad. And then so that, after running the second line, this is still right before. We have this, x squared. So the second derivative of this is just 2, no matter what. But the answer is 8. What's going on? Where's this number coming from? No, no. We actually just learned this. Try to make sense of 8 as a combination of the actual value that you expect it to have, which is 2, and then something floating around over here. Yes, yes. Py PyTorch always creates a ghost, right? Whenever you run the backward, it creates a ghost. So make sure that you do this. Okay. Always before the second run, make sure that you do this. So now, after those 2 modifications, we finally got the correct answer. Yeah. This is very, very, very important. I've seen many graduate students under miserable, stress because of those, typical mistake. Because even without those, the code runs just fine. Okay. This one, at least we know the answer for the first derivative and the second derivative because the function is simple. But imagine this was some crazy neural network whose analytic derivatives we don't know of. And then it spit out some number, right? And as a student, you just trust it, right? My computer told me that the derivative is this. Okay, sure. Okay, must be the second derivative and the first derivative must be the same, and then move on, right? It's extremely hard to debug. Okay, it's extremely hard to debug. Be very careful. Always make sure that you know. First of all, clone. Okay, because otherwise it's a reference, and then each time you run backward, make sure that you zero out. Okay, so that you get the correct number. The first good? Yeah. So if this makes sense, then no matter how complicated your function is, now you have a really powerful tool, not only for neural network training, but also for other research applications. Like whenever you need to take derivative of something, go to PyTorch, and you can do this. Um, so no matter how complicated your function is, PyTorch should be able to take the derivatives as long as the function is differential. All right. But I just told you a very, very, gave you a very useful tool, not just for the purpose of neural network training, but also for everything else. How am I doing on time? Okay, so now, if this makes sense, we're going to go one additional step forward. Okay. So with this one, you can do pretty much everything as long as your function is scalar value. But what if your function is a vector value? Is the next question. So unfortunately, the bad news for you is that for vector valued functions, this exact same thing is not going to work. And there's a different set of, library that you have to use. Okay, is the first thing to remember. So in our case over here, this scalar function over here, after taking the first derivative, that first derivative itself is still a scalar function. So we had no issues. But let's consider this particular case. Now you have x which is 2. require grad true. And then say y, and let's say 3. And then my function f is x times y plus exponential of y plus x or something like that. So I have some, function like this, still a scalar function, right? Because as a result of computing this, we have a single number. Agreed? So half the backward, and and you may wonder, print x dot grad, y dot grad, right? And in this way, you can compute the first order derivative, and you actually got it, right? And if you want to check df dx is y plus 1, right? And df dy equals to x exponential y, because y dy, and then the last term gets ignored. So this is analytic derivative, which is exactly the same as what PyTorch computed. So far so good. So that was just a sanity check. But now, let's say it's actually df dx equals to x dot grad dot clone. Df dy is y dot grad dot clone. Then the same thing. Let's make it better. Now, your hope is to be able to compute the second derivative. So you may want to do something like create graph true, right? And then df dx dot backward, df dy dot backward. Well, let's just do df dx dot backward. And before we do that, don't forget to zero out x dot grad and the y dot grad. Right? And then, by taking the derivative of df dx, we have d square f dx square at x dot grad, right? And d2f dx dy, right? In y dot grad. And print it to d2f dx2, d2f dx dy. What? d2f dx2, d2f dx dy. Yeah. So you should be able to follow the logic here, right? Where we start from the function f, and then computed the first order derivatives. And then we computed the second order derivatives like this. And then finally, we have the second order derivative of f with respect to dx 2 times, or second order derivative with respect to x once, and then followed by 1. I have, instead of this, I should just create a, now I have torch, rend, and then say 100-dimensional vector. Well, that's too ambitious. Let's go with 10. 10-dimensional vector, and then my function f is, let's say, torch dot sum of x square, maybe. Yeah. So we have the squared Euclidean norm of the vector x, right? So have that backward. Have that backward. Create graph. True. We'll give you, df, right? Which is x dot grad clone. Let's run it thus far. Oh, actually, yeah. Mm, mm, mm. Yeah. So far so good, right? We have a scalar valued function, and then we were able to compute the gradient of that scalar value function, and the gradient is essentially just 2 times the input vector. So if you want to do the sanity check, just print 2 times x, and you will see that the numbers are the same, right? So far so good. Everything works fine. But now let's say, you want to take the second derivative. And to do that, you would probably want to do something like this, right? But when you run this, it's going to complain by saying grad can be implicitly created only for scalar outputs. And that's because, unlike the situation that we saw before, now df is a vector. Previously, the derivative was a scalar, so that we could keep taking the derivatives of the scalars. But now, since we have this gradient df, which is a vector valued function, now if you try to take the derivative of this, then PyTorch will start to complain about it, and then say, backward only works for scalar valued functions. So instead, a more desirable and more versatile way of computing the gradient is, instead of calling the backward, you could do torch dot autograd dot grad. Okay. And then the name of the function that you want to take the derivative of. And then the the variable. Okay. And that I'm going to call grad. And this function will compute the gradient. And if you want to do the sanity check, compare that with the analytic derivatives. So they're the same, right? So it'll compute the gradient, the function f, with respect to x, in the more or less the same manner. Okay. Now notice that we haven't used the backward. Okay. And because of that, if I print x.grad, you'll see that it prints non. Okay. So internally, we're using kind of different, module to construct the computational graph and, blah, 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 right? And that's why, x.grad doesn't have, anything inside, even if we, computed a gradient. So it's a slightly different use, okay? And I personally prefer this one over backward, because backward you have to clean up, and things can be a little messy in terms of housekeeping. But with this one, it is so much more, I guess, so much cleaner and easier to handle things. Now, another benefit of this guy over here is that you can also compute the the derivative of the vector value functions. So let me hold 1 second. Let me so now this is where this becomes more useful. Oh, 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 oh. Hmm? Actually, grad outputs. Bear with me. Yes. So on top of what we already saw over here, the first order derivative. Now I use torch.autograd.grad to compute the second derivative of the given function. So recall, this is just the sigma of the square of the individual elements, right? And the first derivative was supposed to be, 2 times of x. Now, if you take the derivative one more time, right, with respect to each value, then you have 2 as an output, right? And this is exactly what we got from running the torch.autograd.grad, okay? Is the first thing that I wanted to show you. Now, in terms of the syntax, this is a little more sophisticated, but once you understand the syntax, it's not, too bad. So it's the same in that torch.autograd.grad, you put the function, which this time is the gradient because we're taking the second derivative. And then here's the variable where you want to, evaluate the gradient of. So far the syntax is the same, but then, after that, I added this part over here. So grad outputs is a flag for autograd.grad algorithm to say that now I'm taking the derivative of some vector valued function. And then for that vector valued function, I want the outputs to be computed and stored. Okay. So you have to turn on the grad outputs flag in order to be able to compute the derivative of the of a vector value function. This is the first thing to remember. Now, what is this part over here? Grad outputs equals to torch.ones like x. So as the name of the function indicates, what this thing does is to create a PyTorch tensor that is of the size exactly the same as x, okay? And then what we're going to do is to fill that vector with ones, okay? So we're going to create a vector that is the same size of x, but then all the entries are filled with ones, is what the torch ones like will do. Now, in summary, what happens over here, is, I cannot write on this, right? So I have to. Yeah, I miss the good old days where we used to have the physical boards, so that I can compare the code with the. But we started with the function f. We started with the function f, which is the sigma of xi square, right? The function df essentially partial derivative of f with respect to the first variable, second variable, third variable, right? Is what we get. Now, technically, the square f should be this first guy. Okay, so df This first guy, derivative with respect to x1, which is 2, which is 2. Again, this first guy, derivative with respect to x2, which is 0. This first guy again, derivative with respect to the third guy, and we're going to have a bunch of zeros over here. And then the second row of the second order derivative is the derivative of this guy with respect to x1, which is 0. This guy with respect to x2, which is 2, and then 0, 0, 0. And then from this pattern, you will see that this is going to be a diagonal matrix, right? Which is essentially 2 times identity matrix of 10 dimension, right? So this is the rigorous, second order derivative of the vector value function. Now the problem is, like I mentioned earlier, we do not handle the actual Jacobian. Okay. Instead, what PyTorch does, so this is our Jacobian. What PyTorch does is to compute the Jacobian vector product called the VJP. Okay. So instead of storing the actual Jacobian, PyTorch will store that VJP, and therefore, what PyTorch expects, okay, when you compute the derivative of a vector value function, is not only the function and the variable, but also that vector is what you have to supply. Okay, so if you have a vector value function, then what you're going to need is the function itself and the variable that you're taking the derivative with, and you have to specify v, the vector Jacobian product. Now, one very clever thing that we just did was, since we're interested in the diagonal components, okay, we passed vector v to be a 10-dimensional vector filled with ones. Okay. So in terms of the vector Jacobian product, when this matrix gets multiplied by ones, you're going to get the diagonal components. Okay. So that is really the line over here. Okay. We have the function that we're taking derivative of. We have the and as we saw, that second derivative was all filled with twos. And that's how we got the result. Okay. So with that being said, my v doesn't have to be that. So for example, if I set my v to be torch ones like, zeros like x, and then if I put v over here like this, then foolish enough, I'm going to be multiplying 0 to a Jacobian, which will give you zeros. But for example, if I set v0 to be 1, then run the code again, then it'll flag up to. So this is actually my first row of the Jacobian. If I'm curious about the third row of my Jacobian, I do this. And that's going to give me the third row of the, or sorry, fourth row of the Jacobian. If you really, really do need the entire Jacobian, then you repeat this process n times and then construct all the n rows, right? So that's, you know, really the crux of what's happening. So there's a little bit of, you know, complexity here because of, mostly because of the math, right? But once you understand the math, it's essentially this: torch.autograd.grad, the function you want to take the derivative of, and then the variable that you're interested in, you know, taking derivative with respect to, and then the vector in the vector Jacobian product. So in that way, now let's just do one more example before the break. Let's say you have your machine learning model X, model, and then the model, no, I cannot think of any fancy, you know, well, actually, W equals to torch dot rand, and then let's say 10 by 10. And W at X plus B and then X equals to torch dot rand and dimension. So Y equals to my model X, print Y. Let's see if it, okay. So this works fine. Now, you know, let's say I want to take the derivative of this guy. So what you need to do is torch dot autograd dot grad, right? And then inside of it, the function you want to take the derivative of, and then the variable, right, that you're interested in, and the grad outputs, or the vector. So vector B here, I'm going to be torch dot ones like, and that's like gradient. And if I print gradient, I'll get some gradient. That's, oh, I forgot to, X requires grad. Yeah, now we have the gradient computed. This being a linear function, this being a linear function, the derivative of this function with respect to X is going to be simply the matrix W. Okay. So if I do this and get the first row of that gradient, that's got to be the same as W, not the first row, actually, first column, isn't it? Yeah, first column. So zeroth column this and the grad should be exactly the same as expected. Yeah. So now you have the tool to compute the gradient of or derivative of whatever function. Okay. Now, whatever complicated function you have, now you have the tool, okay, to take the derivative. After the break, what we're going to do is to use this to finally build the physics-informed neural net. Especially, we're gonna play with the harmonic oscillator example. So we're gonna write a simple neural network, and then on that neural network, we're gonna take the derivative of that neural network 2 times, and then plug that into the harmonic oscillator equation, and then we're gonna see how it works. So thank you all, and I'll see you right after the break.